Hello everybody, welcome to another stream. Why haven't I got my stuff set up? Bing. Welcome. How are we all doing? Welcome to another stream. So last stream, we started pouring the CPU implementation of the BVH building process to the GPU. So we didn't actually port... Sorry, I'll rephrase that. Right, so on the screen what we're seeing is a binary tree, which is constructed on the CPU where each node is independently calculated. Like the children of each node is independently calculated. So this will port straight to the GPU. We didn't port that to the... So we're porting that to the GPU today. And what we're also going to do is make it a quad tree as well, because we've got that code as well, which independently converts a binary tree into a quad tree. What we got started on last stream was writing a shader which uniqueifies an array. It's a term I made up. Should make a pattern on it. But yeah, it's called Morton Code Uniqueify Multi-Threaded Uniqueification. Pretty good. Yeah, we made that up last stream. So this stream we're going to construct a BVH, which is going to hopefully be pretty decent. It'll be able to be optimized a bit more, but from the data structure point of view, it should be pretty good. So we need to build a binary tree first, since we cannot build a quad tree right away. But we've got on the CPU side... So what we just saw on the CPU side was that binary tree being as a debug visualization. There's also a quad... Yeah, I got this function called quadify, and it turns that binary tree into a quad tree by starting at the leaf nodes and going up to the parents. So we'll be able to port to GPU quite easily. So this is the quad tree version. So it's able to go... So by dragging these leaf node counts around, we're fully verifying that this algorithm does work. And it's verified with some assertions. So we're able to traverse from the top of the tree all the way down to every single leaf node. So yeah, we're getting this up and running today on GPU. Hey there, Pete. How's it going? Thank you, sir. Egotist, welcome. How you guys doing? Yeah, so pretty exciting stuff. Because, yeah, this was quite complicated, but I'm happy. I'm happy where we're at because it's just it's been proved. So we just have to implement it. So what's great about this quadify algorithm is that it starts at the leaf node, so the four nodes are more likely to show up at the leaf nodes than they are the root nodes. Basically. So yeah, I think it should be good for BVH traversal. I think there's better ways we can optimize the tree, but it's a good first step. So let's begin on the pouring that code over, I think. But yeah, how have you guys been? What have you been up to? I just got back from a family party. We just I'm about to sneeze. I think it's gone. So some extended family, just got to see them first time in like 10 years. So it's pretty good. Good catch up. But yeah, that's what I've been doing today. Obviously went to church as well. So what do I want to call this shader? So what's the process again? So here, we're just going to port it. So it's from that paper and blog post. We implemented this paper. Did a right boring weekend for me, but I consider that good. Amazing. Yeah, it's not as good just to do nothing and rest. Let's take those opportunities where I can. But yeah, these are the links we've been using to build this, to construct this binary tree, which we're going to turn into a quad tree. So basically, we need to design the data structures first, innit? So let's go into the shared header file. So I've got this thing called a BVH node. I made this and I packed everything. I was like, this is amazing. But we can't construct this right away. We've got to create a temporary tree. So I just got to figure out. So I call this the BVH node. It's a binary BVH node, I think I might call it. So this one, from my understanding, is that so they're going to be left and right of each other in memory because they. Oh, is that true? No. The children won't be left and right. You need two indices. Yes, you need a parent. You don't need any information about the ellipsoid in there. Because that gets constructed only for the quad one. So I think we just need to know. We just need to know about the. Do you only need to know about the parent? You might only need to know about the left child. And how many bits do we pack? Use a full 32-bit int. Right. We do more than 64. Yeah, right. So I think we might need to know about the left node. We don't need to know about the right node index because we can know if it's the right node by checking if it's not equal to left, basically. And we only need to know the parent index because we're going to traverse up from the bottom. So from the leaf nodes, we're going to traverse up the tree on the GPU and build the quad tree. So I think with that information alone. Oh no, you do need the right node. Because you need to know. Yeah, you need to be able to get somehow turn that node index into a. Yeah, I'm going to look up tables. I think that's the information we need. We just need a tree. Can you pack any? I don't know if you can pack anything with this. Yes, I think this is all that we need to do. So we can just say, you know, used as, so a binary tree is built on the GPU initially. That is then turned into a quad tree. AKA the BVH node. Struck below. So we just need to make an array of these boys and girls. And then, and we can, awesome, good to hear, Pete. Good to hear, my friend. Right, BVH build process. So what we'd like to do is, so in the buffer, the leaf nodes go at the end, and the internal nodes go before. Yeah, so I guess we'll just call these BVH binary nodes. Or BVH binary node. I think I love the word BVH at the beginning, to be honest. So I'll call this the BVH binary nodes. Yes, so we have that buffer. So let's initialize that buffer quickly. quickly. Right. Neat. So how many nodes are we gonna have? So right. So the number of internal nodes for a binary tree. So if I was just to run the, actually no, wait. Let me just 2 seconds. Here it is. So we have a binary tree, like so. All of these leaf nodes here, so the ones without children, obviously, right? To work out how many non-leaf nodes, aka internal nodes, so these boys and girls, right? It is the number of leaf nodes take away 1. So that's how you work that out for a binary tree. So we're just going to go ahead and write that in. So as simple as number of leaf nodes that we could possibly have in a BVH. Take 1. So maybe I can say, just label it internal nodes capacity, which is BVH leaves cap take 1. Neat. Yeah, I guess if we wanted to have a null node, we could just, treat the 0 as a null node, but I don't know if we need that. Think about it though. So that's pretty good. So now let's get back to the shared header. I want to find that BVH section. Here we go. Here we go. Wait, so we have the BVHs up here. Interesting. Why don't we get all these ladies and gents and bring that into the BVH section. This is the whole, it's pretty cool. I like this one. I like what we made here. So we've got our binary node that we're going to construct temporarily on the GPU, and then we'll turn that into a quad tree. Here's our quad tree design. It's all packed. Each node is an ellipsoid. So it's ellipsoids all the way down with a possibility of up to 4 children. And it does the top level and bottom level BVH as well. So maybe I might revisit some of this. But yeah, we can have a think about this when we've built the tree today, because I think we'll be able to build the tree before we finish the stream. But what I mean by that is like the resolution of his half width and half height, and how. What is the resolution of a of the local space, and then the world? Like how do we? Just make sure that's all okay. I think it will be. I think it will be fine. But yeah, we've got ways to like initialize a node and then unpack certain aspects from it and get the ellipsoid out in. So I'm pretty happy with that. But we want to make a new thing. So this was called BVH construct. Right, so it can't just be one shader anymore. There's me trying to so we want to do a BVH construct a binary tree. So we've got the multi-code uniquify. The multi-codes are also sorted as well. Sorted, uniquified. And then construct binary. Or BVH binary construct. And then, so we want the output binary nodes. With all the leaf Morton codes. We'll we don't really have a node start index because we're not. It's just in a temporary build array. The nodes will get deposited into some big heap of nodes in the final construct. So we just want to say number of leaves. We'll need some more stuff though, but at least we've got it shaping. BVH binary construct. Oh yeah, here we come. I remember writing a BVH algorithm as part of my first C++ project, and it was a terrible implementation looking back on it. Yep. Yeah, it's cool. My first one was a binary. I ended up doing a binary heap because so it's perfectly balanced, and I can address. I didn't have to store any indices. I could just take an index and instantly convert that into another index. You know, I could convert it into a parent. I could convert it into a left or a right node just with maths. Binary heaps are quite useful, but they're not really good for a BVH. Because you want it, from my understanding at least, you want to have some stuff go deeper than the rest of it, just because that way it's more locally stuff that is linked to each other will be closer locally. Whereas if you have a more of a perfectly balanced tree, you'll be yeah, from my understanding at least. I think that's the way it works. Because obviously if it's perfectly balanced, it's more you won't go down such deep chains. Which would be computationally worse. Like, because you spend a lot of time traversing down. But there's... Yeah. I'm not quite sure on that one, though. Maybe. Because if it's perfectly balanced, you'll be testing against things which are you're not even near, I think. Or the way they get groups, the bounding boxes would be a bit bigger. I think that's it. From my understanding. These things are complicated. Trees are complicated. Like, they always fry my brain. I gotta understand it fully before I do a devlog on it though. But yeah. It's quite crazy though you did a full BVH algorithm for your first C++ project. Did you do a lot of programming before that, Pete? Sounds challenging. Very challenging, to say the least. Alright, so I think we need... So we need to really... Holy what? I already got common upper bits. Yes, I think that's the way it works. You do a... Yeah, count leading zeros. Yes. Yeah. So on GPU, we don't have a count leading zeros intrinsic, but they probably have it in hardware. But yeah, you have to. I think they do it on NVIDIA. I'm not sure about AMD. But yeah, so we use what is the index of the most significant bit that's set, and then we do one take of that, and that gives you the count leading zeros. So how many zeros from the left-hand side is there? It's part of the that paper. So determine range is the next thing. Just find it. This is it here. So I'll convert this code over to GPU, no biggie. Easy peasy. So what do we need again? Internal node index, number of leaf nodes, neat. Right, it seems to have worked. Seems to be pretty alright. It just does some searches for the range. So picture-wise, given a node index, given an internal node, which is one of these, right? These orange ones, you can work out the range in which its descendants will be. This one will give you a range of 2 and 3. 3 will give you a range of 0 to 3. That's what this code does. Pretty clever. It's probably about as complicated as you want code to get, to be honest. Yeah. So that's all tested and works. So that's the determine range function. We need another one which does the split. What do they call it? What do they call that again? Find split, yeah. So this find split, which I got implemented here as well. Yeah, I was pointing something from another language called Blitzmax. Ah. I've never heard of that language. Interesting. What a long name for a programming language as well. Right, it runs on a bunch of things. It's meant to be like basic or something where it's quite simple. Yeah. I don't know what to call this, to be honest, but yeah. Interesting. Never heard of that. It's an old language that has roots in the Amiga days, probably before your time. Interesting. It does look like some of the modern languages kind of look similar to that. But yeah, it does look like it's got some Pascal type elements to it as well. Interesting. There's a lot of languages. That's why we need more. Holy crap. How was I writing this? Yeah, so return split. Int split. Right, so what do we need to be passed into here? So we need the mort codes. We want a U32 times 2 of range. And that's about it, I think. Right, so does this still compile? No. Right, internal node index. Yeah. Sweet, so that compiles, that's good. So now we've got those two major functions. We can now port over the code that does the tree, the binary tree construction. So that is this part here. So this goes in the shader, wherever that shader is here. So we need to call those two functions. So there's that determine range, which gets you the there's a determine range which gets you that. So if you get an internal node of 3, it gives you this sort of block here from 0 to 3. If you go 1, it gives you 0 and 1. You get this 4, it gives you a 4 to a 7. And this changes based on how the Morton codes are for the leaves. And then there's that find split function, which takes that range and finds where do I split this tree down. So between 1 and 2 at this point. Obviously, this splits between 0 and 1. 5 splits between actually 4 and 5 in this case. So it's a bit of a different, the way this one's built very classically, whereas this kind of, yeah. 4 is actually outside of, 4 is actually a sibling with this internal node of 5, right? Rather than being the leaf of this one or whatever, yeah. So we get the range out, determine range, passing the Morton codes, leaf node Morton codes, leaf nodes count. The internal node index. So we launch for every internal node. So you can get the number of internal nodes, which is leaf nodes count take 1. So what we're going to say is if the dispatch index, which is going to be our internal node, right? If that is greater than or equal to, then return, because remember we're in a compute shader here, and you can have 32 threads which are, it launches in groups of 32 threads which run in lockstep. So obviously some of those threads are going to go over the edge of the number of internal nodes. So those need to become inactive. So we return there for those guys. Then obviously we put in the internal index, which is SV dispatch. So now it's the job of this shader is to link up all of the internal nodes with children nodes. So obviously some of the internal nodes get leaf nodes, and you construct a whole tree that way. So in split, we'll call it, and then find split is the function. So that you pass in with the range into there. Yeah. Neat. So basically we need to get that binary node and then put it in there. So I think we could construct it locally. Where's the parent? All right. The parent's never written to. Yeah, we've got to be careful. Yeah, the parent's written to by the. So we have to make sure that the memory is at least. What can we do? So every thread accesses. The thing is, you've got to be careful because what you want is that root node. So the root node is always 0. So what we can actually say is if the root node, if we're 0, we should write to the parent, basically. So if we want to say, oh, by the way, that where the hell are you? Yeah, BVH binary nodes, right? So we go, okay, well, parent index, I guess I called it. We'll set that to the invalid one, which is going to be 32 max. And then down here we can just set all of those properly. So BVH binary nodes. Right, so rather than using that, what have I even done here? Go to the get the children index, and yeah, this is all a bit funny. So let's correct it in a bit. This came from like just getting it working, so we can clean it up now. So basically we would want to produce a local variable called internal index because it just makes it more readable, right? So let's do that. It's only a few places, right? So internal index, how about we call you internal node index? Makes it a little bit more readable. Right, so alright, it's good. So here's where we give that left and right. Left and right is just +1 always, because the way it's made, left is always just 1 plus. So right is always 1 plus the left. So realistically, we can squish that into 8 bytes. Isn't that amazing? Left node and then right node. Oh yeah, it's 8 bytes. Here we go. So basically we just say, all right, left equals split. And then what we're saying is if, oh no, we can't. All right, back to, we can't do that. And the reason is because this scenario here, these leaf nodes, even though they're labeled 0, 1, 2, 3, 4, whatever, they sit after the internal nodes. So this is actually 7, right? 6 is there, it's the biggest internal node. This is 7, 8, 9, 10, 11, 12 in the array of nodes. So this is what this code is doing here. I should link to the paper and blogs in here is a comment, I think. I'll put a nice comment in there in a bit. Yeah, so we're saying right on the right. So realistically, we're like left node index equals split, right node index equals split plus 1. And then we just do, so I'm just doing it like that. And then these guys will be like, well, alright, so we make those better. Internal nodes count. Alright. And then we fill in, we populate the binary node with the correct data. And then here's when we, so since you're always building an internal node, it means it always has 2 children. Always. So we access the left and the right, and we make the parent index be us. Neat. That's simple. So now I think we should check it's compiling, then write some comments. Hey Chrismania, how you doing? Oh Mana. I like to pronounce people's names wrong, it's my thing. The butcher of names. How are you? Right, so what I would like to say is like this is okay. Construct a binary tree. Using I think this is effectively the L, is it LBVH? The most promising current parallel is the so-called linear BVH. The idea is I think it's linear BVH, isn't it? So I think this is that linear BVH tree. We're first to present I think this is a linear. So it's not really. It's a newer version of that linear BVH. It's slightly different. Right, it's not even write that in there. Using the following sort of blog and paper, using the technique from the following. Later, we turn this binary tree into a quadtree. To yeah, because we're packing more nodes, we're packing more nodes into a single cache line. Something like that. That's the idea, at least. Right. So here we just need the tree information. We just need the tree. Need to build the links between the tree nodes. Awesome, good to hear, Chris and Mana. Yeah, I'm doing good. Just came back from a family get together, saw some extended family that I haven't seen for about 10 years. That was cool, catching up. Things are going good. The baby boy just started crawling recently, so he's been shooting across the room. And he's also just learned to say no as well, literally like a couple hours ago. So that's quite funny. He's like, no, and then points his finger. So yeah, he's great. So yeah, we're just getting used to him crawling now. His past few days has been crawling around in bed and not going to sleep, and then sitting up against the door, just waiting for you to come back in. So yeah, we've been dealing with that at the moment. Yeah, things are going good. I've been a bit tired, to be fair. Need to catch up on some more sleep. So yeah, I guess we want to say like we dispatch a thread for each internal node of the tree and find both of the children. Yeah. Both of the children independently. Man, spelling independently. Yeah. Without by scanning over the sorted. By scanning over the sorted Morton codes. Yeah. So this is, find the range of nodes that find the range of descendant English descendant nodes, find the range of descendant nodes leaf nodes that for this internal node, right? So, and then you basically want to find where, find the split, find the left node, aka the split, find the left child node, aka the split point. Right, and then this is basically saying, that's quite self-explanatory. Finds the leaf node. Is there anything else I can say? Right, then here we want to say that, if the split is equal, if the split is fully to the left, to the beginning or end of the range, then make the nodes target the leaf. Or then this means right, then make our children the leaf node. Make that reference target a leaf node instead. Target the corresponding. Correspond. Damn it. Yeah, target the corresponding leaf node instead. Right. And then this obviously just assigns sets up the binary tree. This obviously sets up the parent. We don't have to comment about that one. Right, so I think that's good. That all compiles. So that we just want to just launch that now and construct that on the GPU. We can, yeah. Where do we do that Uniquify stuff? Right, so we've just put in a bunch of random, right, V Morton codes from the CPU. Right, so let's get in here and do another one of these sorts of thingies. This builds the Morton, sorts the Morton codes, mem sets the new array they get copied into, uniquifies them from one array to another. So there's no duplicate Morton codes. Then we BVH construct so also why binary construct. So we'll get these boys and girls. I think I want to uniquified. Hey Isaac. Oh, Isaac. Yeah, trees are hard, man. So you get dizzy, I know, right? Yeah. I just about understand this myself, but it's very difficult for me to explain. I need to nail it. I think next stream I want to record a devlog for this. But yeah, I need to get my head around it again, and so I can describe it fully because it's pretty clever, and I'm usually quite scared of clever code, but it's okay because it does a it's not yeah it's pretty clever, but it's not so complicated. A little bit complicated though. I think the trade-off is I think what it's achieved with the complexity is worth the trade. But yeah, it does make me it's a bit confusing though. It would be nice. What would be really nice though, is if I could describe it all in my code base, but I've had to link to external resources because it is that complicated. That's the only downside to it. Yeah. But, you can't keep all the knowledge in your code base. It's impossible. Hey Cat Pain, how you doing? I was born dizzy. Oh yeah. Things are complicated. Takes me ages to figure out stuff sometimes. Amount of reading I do, and then like, I think I best understand stuff when I implement it. Gosh. Um. Hmm. Number of internal nodes. Does this take 1? And then you need to basically use that instead. Alright, so that should launch and work. Shouldn't mess my GPU, hopefully. I think we built that thing, right? So I wanted to rename... Yeah, I made the buff, which is good. Wait, is it size of U32? Good catch. So I actually wanted to rename this quickly. I want to prefix it with like the word BVH because it's what it's for, man. So it's just for the leaf nodes, isn't it, as well? So leaf node Morton codes. It gets a bit long at that point. Yeah. I think that's right. I don't do it. Okay, that's good. So should we try and launch that? Hope it doesn't fry my GPU. Sometimes complex problems have simple elegant solutions, but actually most of the time complex problems are quite complex solutions. Yeah. Yep. Especially trees. Yeah. Especially trees. Right, if my stream dies, I'll be right back, but it shouldn't do, right? Because we tested it all on CPU. So I'm pretty confident in that. Yes. So as I move this around, it's actually changing how the GPU one works as well. This is the quad tree version. We've only just constructed the binary tree one. So let me just we're gonna verify this. We're not just gonna be like, oh, it works. It'll be quite easy to verify with a smaller tree. But let me just get in there and find the here it is. So this is just going to debug visualize the binary tree. So this is what we constructed on the GPU just now. And it's working. But let's just verify it's working. So this is the tree that we're going to verify. I can just press, is it F12? Yeah, I got a screenshot now. Go into the game, and here's my screenshot viewer. So basically, if we open up the screenshots folder, here it is. So we can close the game. Well, maybe I didn't need to do that. Or did I? So I'm going to run a dog. And we're going to inspect the memory. Let's make sure the references are there and they'll make sense. So it's on the capture. I think I'll trust it on that one. And we're going to find, yes, on the first frame it only does it actually. So we're going to find, I think it's pass 2. This is where all the BVH stuff happens because there's some barriers in here. We fill the Morton code buffer with a bunch of zeros. So somewhere in here, let's give it a go. Oh shoot, what happened? Oh, it's just my laptop battery, my laptop Wi-Fi disconnected. Hopefully that connects back again. Bit of a bugger. Limited connectivity, what? Right, I'll restart my laptop then. Right, can't see the chat. Stream's still going though, right? Yeah, neat. Cool. Anyway, so getting back to this, so somewhere here, yeah, BVH binary construct, awesome. So in here we will reference a barrier, so we'll put a barrier on, what's this one? Binary nodes, perfect. So we view the contents. We're going to put a data structure in here, let's just quickly type it out. BVH binary node. So we actually have 3 indices. So uint, parent, uint, lift, uint. Alright. So yeah, we're gonna chuck down the new BVH binary tree. Click a save on that one. Let's save that. Apply. So here's the data. We're just going to make sure it references up with that image we took earlier. What's going on? This looks a bit incorrect. Zero should not link to 1 and 2. Let me look at that data quick, make sure I got that right. Yeah, 3 ints. Right, awesome. Right, so something appears to be wrong. No, my plans. So what have I done wrong? Right, so you got a 0 up there, a 5. Oh, for crying out loud, why's my laptop not? Great. My router's being a piece of crap, and I'm streaming now, so I can't even reset it. So I have to peek back at chat every now and then. Well, that goes down the toilet. Goodbye laptop. I did my phone. Maybe my phone will be the I go back to before the days where I used my laptop. I can get the channel here. I'm like an old man now trying to use a phone. Yeah, what Wi-Fi is dead. I'll get the Twitch chat on my phone. Oh, it went straight to me. Why? Live chat only, please, before my data gets absolutely chewed up by this thing. And we're back. Chat's on my phone. Right. Neat. Anyway, back to here. Why is my data wrong? Element 0 should be the root node. Can I chuck you over? Use one of that. Yeah. Right. Put the chat over there like that. Right, so my laptop is a glorified phone stand now. Okay. Yeah, so we've got these Alright. So apparently, so why has 2 got a child between? Ah, right, here's the numbering. Yeah. So the leaf node. Oh, no. Yeah, the numbering should be the same. What is up with this numbering? Alright, I think the numbering could be wrong in CPU side. Because the left-hand side should be like 1, 2. Oh, it is 1, 2, 3, 4, 5, 6. And then the leaf nodes 1, 2, 3, 4, 5, 6, 7, 8. Yeah. Okay, maybe this is correct. So when we talk about this root one, are we even right? Oh, you know what it is? Do we need to go after this thing? No. Oh, are we right now using the internal index? No, it should be right. Hang on a minute. So if the internal node index is 0, it should write out E32 max. I don't see that there at all. So it must mean that something might be writing. Is something referencing. So we've only got. What is that? Maybe we can't trust this. You know what? I could be viewing the wrong buffer right now. This buffer seems like it's linearly increasing. This looks like the Morton code buffer. Did I click on the wrong one? It is. Right, I clicked on the wrong buffer. I interpreted the data wrong. My life. Right. Okay. Where is it? Pipeline, compute, here we go. Binary nodes, that one. Alright, we're on the right one this time. Alright, this looks better. Okay. So the thing to take note is how many nodes did we have? Well, it's hard to know. These numbers feel a bit wrong. 60 odd? There ain't 60. Oh, wait. It's done once when we boot up the game. So it's whatever the default one is. Crap. Alright, we need a new screenshot. Well, I don't really need a screenshot, we can just run the game. So whatever the default one is this one here. I'll take the screenshot because it's way nicer. On my... Alright. So, here's what we're dealing with, I think. They're a bit high still, though. Did I do this? Um, 128 Morton codes. Okay, it's completely different. It's not even linked up to the thing at all. Right, so where's that tree thing? There's quite a lot of them, to be honest. But we can at least follow a few and just make sure it's correct. Where's the slider? Here in it. That's PBR mode. Right, so 128 leaves is 128 more codes. So run that. Right. This is what we've got on a GPU. So if we, I guess we'll take that screenshot quick. So we'll follow this one around. '63, '64. This still looks wrong. Why does it look wrong? $128 leaf means number of molten codes. Yeah, I think this is launching fine. Number of internal nodes, does that take 1? That's what you're launching. You launch over all the internal nodes. Number of leaves is set up correct. So why aren't they the same? Why should they link to... we ran a uniqueifier on it. Oh, they got different rand. They got different random numbers. Right. Good one. So different random numbers. So to sync up with what the crap is going on here, where's that static array? Here, right? So we run that every frame and we generate the same. Randomly generate, where's, oh yeah, it's a fixed seed. That's why it works the same. So realistically, we'll put this here and then we'll, let's figure this one out. So where do we upload it to the GPU? It's right here. So we'll just do the mem copy. Well, I got a thing in my code base where I say core copy element many, molten codes, this thingy, BVH molten codes count. Right, so this will be, so we've got to do another capture. Just double check that still runs. All right, so you know what? Now we're doing another capture, let's just make things more sensible. So let's just make this instead like 32, and then we'll actually be able to have more of a sensible thing to check if it's right. So this is what we're going to build on, we've built on the GPU now. I've taken a screenshot as well so we can get that. And we'll run it again in render doc, do a proper capture this time. Well, yeah, do another capture on the proper data this time. And yeah, so it records the first frame. The first frame is when it gets constructed. And then we can move over to the did it really only launch one? Oh yeah, it only needs to launch one group. Did it all on one compute unit. BVH binary nodes. Click. And interpret data like this. Right. And the results seem promising. So let's follow this through and see what we get. So 16 and 17. So the root node is 16, 17. Next line, 1. So the node 1 here has 32 and 33. Nice. The node 2, 7, 31. So parent is 7, yep. Oh yeah, the root of, so the parent of 1 is 2. Yeah, that's correct as well. So 2 has children 31 and 1. Yep. Yeah, we won't go through all of these, but let's just see parts of the tree. It should be. Yeah, it seems alright. Let's go to 3. Node 3 is here. Children 6 and 38. Yep. 4. Parent of 7. Yep. Where's 4? 4 is 5, 37. So 38's there. 37 should be quite nearby. Here. 4. Parent of 6, 5, 37. Yep. 5 is obviously a parent of child of 4 rather. Yep, 35, 36. Yep. We can't really see that one, but let's just assume it is that. Well, no, it will be because it's a leaf node. They're next to each other. Yeah, let's just pick another random one. 28 has parent of 22. Yep. 59 and 29. Yep. So I think this looks fine. Let's just quickly double check that all the nodes are written out. Yeah, goes up to 30. 30 what? Well, yeah, so the children, the leaf nodes don't get the children set. So we could actually just mem set the whole thing to U32 max. But you'll be starting off on the leaf nodes anyway, and you'll just be traversing up the parents. So the leaf node indices will be invalid for, yeah, so I'll write that in the data structure as a comment. Because it's just an optimization, basically. We could just save writing out that memory if we don't have to. So we'll say that these are uninitialized. Currently uninitialized when this is a leaf node. Currently these are uninitialized when you have a leaf node, right? We know when something is a leaf node as we start traversing from the leaf nodes and go up to the parents, up the parent nodes. Yeah. So we start, yeah, and you can start traversing from the leaves quite easily because the leaves are stored halfway through, basically halfway through the array to the end of the array. So it's quite easy to do that. Right, so I'm happy about that. So should we start doing the final shader? So this is going to be doing constructing a full quad tree. So construct a quad tree from the binary tree. Where each thread is I gotta figure it out. But yeah, and calculate the boundaries, and calculate the boundaries, and calculate the ellipsoid, because we use ellipsoids instead of ABBs, because everything's an ellipsoid, so that should help us traverse it better, hopefully. Calculate the ellipsoid bounds. Yeah, and calculate the ellipsoid bounds for each node. We start from the leaf nodes of the binary tree and ascend up the parents Ascend up the parents. We start each thread on a leaf node and ascend up the parents, terminating one side at a time, while terminating one sibling thread at a time. Yeah, we'll start there, and then I guess we'll see what we can add from there, basically. So effectively, you're gonna want this is the destination nodes, and then there's a BVH nodes and there's a BVH binary nodes. I don't know if we need the molten codes anymore. I think we're alright without those. We definitely need to start node indices because basically this BVH nodes is going to be the final. It's a massive array, and we're going to have to heap allocate or do like we're going to have to heap allocate from it, defrag it, all sorts really. It'll be cool. The defrag process will be quite easy, I think. Wait, will it? If we have, yeah, maybe defragging it in place might be quite difficult. If we had 2 buffers, it would be super easy. But yeah, it'll be possible to defrag it. But that'll come later when we have multiple objects. We'll sort that out. BVH change start index. We also need to know the number of leaf nodes, and from that we can derive the number of internal nodes for the binary tree and the quad tree. So I still have to figure out how we're gonna. What do I? Yeah, so we've got an implementation on the CPU. We're going to grab that one. It's called quadify 2. So recursively descends down the tree and then comes back up, and we need to retain a count of the number of grandchildren. And that is how we figure out how to join everything together. Right. So we'll port over this code to the GPU. So each thread is going to get a leaf node and it will ascend up. So we should be able to, yeah, we're going to somehow, I think we need a temporary buffer to store the number of grandchildren in, and then we'll read those back out, something like that. But yeah, I'm just going to take a quick break, get another refill of drink, and we'll be right back. Alright, welcome back everybody. So let's port this qualify code over to the GPU. Where's my music? Yeah, so we start off on all the leaf nodes. So we need to make sure that when we launch this, yes, so leaf nodes count. Rightio. So we're going to get a, this will be known as a binary BVH binary leaf node index. Internal nodes count. Leaf nodes take 1, right? So effectively we need to get, so this plus the SV dispatch index.x will give us a node index for the leaf node. So we launch for every single leaf node from 0 to number of leaf nodes, and this will, all the internal nodes are before the leaf nodes, and we just add on that to that sort of leaf index to get the actual node itself. Yeah, so now you start doing a while loop. So I guess you're saying while this, so I guess you do a do while, and I'm probably going to hate myself for doing a do while. Just you wait. We're not going to keep this do while. It will change. So we're gonna traverse up the. We need to get the. So you get the node you're referring to. You get the parent. So I guess we say BC binary BVH. Hang on a minute. BVH binary nodes, and then we say BVH binary node index dot parent index. So this is the BVH binary parent index. So we can then use that. We've got to somehow, because there's multiple threads in lockstep and out of lock, multiple threads running kind of out of lockstep as well, where they're gonna write to the parent some before the others, right? Some exactly at the same time, and they resolve that. They resolve that case as well. But so we're gonna have to use atomics basically, because some, you look at the picture. Sometimes you've got nodes which are very far apart. So 59 and 29. These are not going to run in the same set of threads in lockstep, but they have the same parent. So they're going to go up. You get this node and you have this node. Yeah, so this node is going to run in one compute unit. It's the leaf node. So it's just going to go up to the parent. It's going to try and write a bit, an atomic flag, and then it will check to say, hey, has my sibling been here yet? And if that flag was not set, then it's the first one to be here, then it just terminates. So meanwhile, you'd have these ones running on this same compute unit in lockstep, because it is a multiples of 32, right? And these would be, so 0 to 31 inclusively would be the first compute unit. these will be part of the next compute unit, 32 to 63. So these will be running, check the parent. These will write the parent atomically with, one of them will end up writing to it just after and receiving the bit back and being like, oh, this bit's already set, so I'm the last one to do this. So I will continue and the other one will terminate. So 60 will terminate, 61 will carry on. So the thread of 61 will then do the same thing again. Try and write to here. Obviously this one wrote to it first and terminated. Second one comes in, writes there, and repeats here, it's the second one to come up here and goes up. So while we're going up the tree, we're also doing more things, but we need a place to write those atomic bits. So where can we possibly do that? Well, we could have another array, but we already have so what I think we should do, we should trash the binary tree nodes. So we make them read write, as we already have. Neat. We're gonna trash them hard. So what we're gonna do is actually do an atomic. While we do this read, I guess we can do an atomic. So we'll get the. I guess it could be like a constant or whatever, right? And we'll call it a. We'll call it a visit bit. So the visit bit will just be the high bit, because we're not going to use that. It's always going to be 0. So there's 1 byte, 2 byte, 3 byte, 4 byte. So we're going to do an atomic OR, bit OR, I guess I call it. I forget these things. We'll figure it out. I think it's bit underscore OR. So this we'll put the visit bit in there, and it obviously reads back what it was before it wrote it. So if the visit bit is present, then we carry on. So if the visit bit is not present, then we terminate. What does it mean by you terminate? Yeah, I think you literally just terminate right away. So if the visit bit is not present, so we want to say like we are the last node, or we are the first node between my other sibling. To reach the parent, terminate here. Yeah. So we need to be building a bounding volume as well. And we need to be somehow linking to the building the quad tree as well. So after this, you can then go up to the parent. So you can then say BVH binary node index equals this, remove the visit bit, and now you've just done this, which is silly. So U32 max is the or we cannot use it in the parent one actually, because U32 max is the right. We've got to set it to U32 max take. Right. BVH binary node null. So I guess we could have done the +1 thing. but I don't know. Invalid, I guess we'll call it. So this is going to be 7f, 1 byte, 2 byte, 3 byte, 4 byte, and then we'll stick the visit bit at the top. Right, might as well visit bit. Hey Captain Chica, how you doing? Hey, oh, I'm a screen protector, man. Hey Lupo, how's it going? I haven't been here in a long while. Have a master Vulkan. Yeah. Yeah, Vulkan's alright. Pretty easy for me these days. Well, yeah, it has its complications, don't get me wrong. And but I know how to navigate it. Things obviously require work with it. It's very complicated, but yeah, Vulkan's cool. Yeah, I wish it was simpler. I wish it wasn't as crazy in places. I wish it was designed better, but yeah, the things it allows you to do is pretty nice when you've written thousands of lines of code. Yeah, it's my hobby project. Yeah, so we're just trying to construct a BVH filled with ellipsoids. We've currently got it working on CPU, and we just point it to GPU. So this is a binary tree that we're building. Let's reduce that down a bit. So here's my scene we've got PBR now. So we've got an ellipsoid. We're switching to ellipsoids from spheres. I want to try and model stuff with ellipsoids. So yeah, we've got a full physically based renderer. So this is an environment map that we got from the internet. And there's a couple of lights in the scene as well, lighting this object, and there's some reflectance in there as well. Yeah, we're just building a new way to render the scene with a bounding volume hierarchy. And we're doing it properly this time rather than the binary heap that we did last time. We did a screen space binning thing after the BVH, and now we're going back to a new BVH. So this is the binary tree version, but we're running the shader which turns it from a binary tree to a quad tree. So it's going to be joining some of the parents up and that. So yeah, it's pretty cool. And then we'll probably move on to writing an editor so we can build some models. But yeah, how have you been, Lupo? What have you been up to? And how's it going, Captain Chica? What have you been up to? So yeah, I think we've sorted that out there where we want to not use U32 max anymore for the invalid bit. And that's cool. So the idea, right, is that this is equal to that with the visit bit removed. Is that right? So how you traverse up to the parent is you get your parent index. Obviously the visit bit has to be set here. If the node is not equal to an invalid node, go up. Neat. So now this is where the fun begins. We now have to actually construct. So we've got the mechanism which allows us to go up the tree. The other sibling will be allowed to traverse up the tree. Okay. So we've got the mechanism which allows us to traverse that binary tree that we built on GPU, starting from the leaf nodes. Every thread gets a leaf node and traversing up the tree where one sibling terminates and the other carries on. So what we have to do now is figure out how do we take a binary node index and turn that into a how do we insert that into a quad tree, basically. So we could just bump allocate them with an atomic add. That's a possibility. So one strategy is bump allocate the indices. The other strategy is just translate the indices. But you don't know how they're going to link up without looking at the data. So I think the best bet is to bump allocate it. I think that's right. So the way it works is that the number of grandchildren, and then you need the node index as well. Is that right? And where the grandchildren sit. Right, so you have that binary tree. And then we'll have this new quad tree. A lot of stuff is such a niche thing nowadays, right? Steep learning curve. I guess so. Like, yeah, I think low level programming is not that bad. Like CPU side, GPU is a whole other can of worms. But yeah, if you're just talking about making a whole game engine like a proper 3D one, it's quite a lot to understand these days. But yeah, low level programming itself just on CPU is not super bad. You can actually make your life quite easy if you know some things. Yeah, there is tons of us. When you get into the games industry, you realize how many people there is. They're just programming away in C++. But yeah, comparatively to probably the tons of programmers, it is probably quite, you could probably deem it a niche. Don't forget learning on Unreal's Tier 3 university course, is it? Yeah, I think understanding if you used to be one of those developers who maintain patches for the Unreal code base, that's probably quite a bit to get familiar with. And that's obviously not what you were saying exactly, but it's quite a big code base to learn. But how's it going, Timps? How you doing? So we've got this binary tree, and the binary tree is gonna like we know the index for the binary tree. The issue is you need to know the quad tree node index of the left. So you can always pass up one of them, but what you actually need to do is store the other one in there. So maybe instead of doing the visit bit thingy, you could atomically you could store, do a compare and exchange, store it in one of the indices. Yeah, all right, here's what we're going to do. I think we're going to change it. Store the quad tree children reference. Is that what we're saying? So as you're going up the tree, maybe it needs to be a temporary array. Because, right, can I describe it from here? Yes, I can. So as you're going up the tree, you're saying like, right, the number of grandchildren. So how many grandchildren is there? We're saying there's two. Even the direct children count as grandchildren if there's just... It's kind of a bit of a weird variable name. But here you're saying, right, how many grandchildren do I have? So we'll say 2. To the right. Oh, sorry, yeah, okay. Start again. So this one will say to the left node, how many grandchildren do you have? It would just be like, oh, there's 1. And then to the right say, oh, there's 1. So in a total we have is 2. So it doesn't do anything. Goes up to this parent. Looks to the left, how many do you have? Oh, I have 1. How many children do you have? Oh, I have 2. So when you do 1 plus 2, you get 3. So when you have 3 or 4, it will decide to get rid of this node and put these 2 children there. So that means if you have go up the parent and there's another single node, it can actually add that on as well and make 4. So it's not just doing it for one level, so we can't necessarily go into the final array sometimes. It can't go into the final array of nodes sometimes because it could go up one more level and it would put 1 more on the end and make a group of 4 or something. So realistically speaking, we might want to put it in a temporary array and then construct after that temporary array. We can bit it afterwards, I guess, and copy it into a proper array. So I guess we just have an array of children indices. You want an array of children indices, and then you can flatten that out into a linear array where you just need one index to reference them. Yeah, I think that's the way you want it to work. Yeah, so what we're going to do is we're going to... I guess this would be called like... So you BVH find all the children. Like quantify find children, quantify construct, where you take all the children, allocate a node. You need a way to have a parent indice as well. Where will the parent indices go? Hmm. I'm going to hit snag in my journey from in real life stuff, so I haven't done many low level things in 4 months. Oh no. What is better performance, storing a single tree in an array or node pointers? Yeah, yeah, so we keep all of our child nodes, so all of the siblings, next to each other in memory. And, well, that's what we're trying to get them into. We're trying to pack them. So we've got just a child index where they're all packed next to each other in memory. So this node is 16 bytes. So 4 of them together fit in a cache line. So that'd be pretty decent. So we're just trying to construct this thing. But yeah, typically it depends on what your access pattern is going to be. Our access pattern is going to be accessing all the children and processing all the children in one after the other. So we're trying to leverage that fact here. But yeah, you don't want to use malloc for a tiny thing. That's true, because malloc puts like a header on it and a footer. It wastes memory. So yeah, you're better off having an arena or a linear allocator and bump allocating it, and yeah, it just makes things way better. Right. So I think the idea is we want to have a temporary array where these quad node things are going to quad tree nodes are going to live. They're going to have an array of child indices, so they're going to be a bit sparse sometimes. But most of the times they'll be kind of linear anyway, so the memory access patterns are going to be quite good. Hey. Oh, there you go. So the memory access patterns are going to be quite good when it comes to copying them into a next to each other anyway. The other thing we've got to resolve is like, so if this whole point of the shader is to figure out how to, so you'll get all the quad tree nodes and get all their children in an array, child indices in an array somewhere. Do you just launch for every quad tree node and then just finish it? Yeah. So you're going to be constructing. So I guess you can call this one construct. So we can construct mostly. Yeah, so I think we'll call this one like construct. BVH construct find children. And then the other one will be BVH construct. This would be like pack, right? Where it's sort of like pack children, where it packs the child nodes. Wait, so each of the nodes are going to be sparse in memory, and then you're packing. And you're packing it also, they become linear in memory. Right, so you're going to be. So is find children a good name. And then we'll have another shader, which will basically be like a refit. So if you're familiar with, where it'll start the root nodes of the quad tree, go up all the parents and generate the ellipsoid bounds. So I think that, and then that means that refit shader is reusable for when we want to do a refit every frame on some animated models. So I think, I wasn't really planning on making this reusable, but it seems it fits into the algorithm that way. So that's okay. Not that it makes it better, it just means we can at least. I was hoping to do it all in one pass, but I can't. So we need another temporary array. How do I implement dynamic lists? Well, dynamic array? What, are you talking about on the GPU? Okay, so we get a quad, so if we just bump allocate a quad tree index, this is going to be a temporary quad tree node index. And that's okay. So in our globals, where's all the BVH build bits and bobs? So quad tree, next quad tree index. So we'll bump allocate, and then some of them you'll get rid of. Is that right? Bump allocate them. Some of them you'll just get rid of. So then when it comes to like copying it or like packing it, I guess you'll just do another bump allocate again. Yes, that sounds correct. So you'd do like a quad BVH next node index, or something like that. So I think it's pretty sensible. So what you need to do is say, so here we set up that we do global. So we did actually write to the globals there, so we need to sync on the global buffer. I just got to double that quickly. Where's the sync? Sync read write on the global resources. Yeah, so we access this, and we say right is equal to 0. So then when we launch that shader next, we can just bump allocate from there. So every time we want a quad node, so you're at the parent, you bump it, BVH quad node index, atomic add, let's take the address here, and we'll add 1 and get back the insert index. So this means we need another array where all the children are going to live, I think. And yeah, so in that binary tree node, I think we need another one where we say quad children, quad node index. So when you look at your right, you know which So these will all have references to all of the binary tree nodes that they want to steal. Right, let me rethink this. There might be a simpler strategy. So if you have the idea is you're trying to make take a node and map it, parent it. So either a node gets deleted and doesn't reference anything, or it gets or the node references is a child of a new quad tree node. So sometimes, so this one will get rid of, this one will stay. This will link to another quad tree node, which we'll find out. Right. So instead we could just maybe make it change the parents, and then you don't need any other arrays. Maybe you could say quad node parent index. So if you just had a bunch of parent indices instead, this could then, so you're just modifying all the children to link to a new parent or something. Then it means that you could go from how could you then pack it properly? So you could then start at the children again. You would then go up to the parent, write a couple of bits to say you've been here, and then those ones can say, figure out which is the last one. Do you use some generic implementation and use void style and these type safety or what? No, we generate the data types. I've got a video on this on the VOD channel. Yeah. So we've implemented binary. No, not binary. Let's get down there. So we didn't do dynamic arrays until we did all the Vulkan stuff. So I wanted to get stuff on screen quick. Collections. Here we go. So if you go to the VOD channel, go to day 111, you'll see us implement a growable array and custom allocators. Then the next day we implement a hash table, and the next day we implement an object pool. And that's what we do basically. Yeah, it's good. It is type safe to a reasonable degree. Yeah, it's type safe. It is 100% type safe. And we have to use macros to forward declare a distinct type for that dynamic array. That's the method we've gone to through. But we don't generate a whole bunch of functions like templates do, because we just use macros which map to functions that work for any type, because they cast to a void pointer version. So it's quite nice. So a quad tree is what people use for collision in 2D. So if you Google for quad tree, you're just going to get a 2D, like it's a 2D version of the octree, and people typically use it for like collision detection and stuff like this. It's like spatial, it's, you know, stuff like this, right, where it subdivides and they can test a small set of objects. We're not doing this. We're just using the fact that it's a tree with up to 4 children. That's all what I mean by quad tree in this context. So it's just it's a BVH tree, a bounding volume hierarchy. So given that we know that the parents, the quad node parent index, if we go up the tree again from the leaf nodes in a multi-threaded way, we can mark the binary node again with some, yeah, so I guess we can use the high bits of this thing. So I guess we need the, it's not, we should call it the temp quad. And unfortunately it's in the, see, but we could just do an atomic add and take some bits. I don't want to. No, because 0, 1. And the fourth one's going to make it overflow. So when you're the last node to write to say you're there, you can then allocate the proper node for it. And then carry on, I think. Yeah, I think we've got to... You say we in your description, are you working on with anyone or perhaps just have royalty ties? No, I like using the word we because I don't like saying the word I about things because I just seems so, it's like egotistical in my opinion. It's like, oh, I did this, I did that. I just like you saying the word we because it's less, yeah. I just don't like bigging myself up too much. It just sounds very, it's pretty cringe. Basically. Yeah. But I've heard arguments the reason why you don't say the word we, so I don't know. I just don't like saying the word I. Yeah, I think we're on to something, but we'll have to. So if we just map the parents, then we can do another traversal up the tree again a second time round. But this time on based on a different one of these guys. So I think we could just call this like quad word 0 or whatever. So we can say quad word 0, you know, where are the you want the parent index mask, so it's going to be stored, we need like 5 bits at the bottom basically, so we're going to say 3, 4, 5, 6, 7, 8. So, you know, we'll just leave a whole byte here. We only need 24 bits really, ain't a big deal. And then we can store like, we'll have a shift here. So we'll move it by just 8 bits or whatever. So what I would like to do is extract out the number of children visit the visit count mask, and this is just going to be the like that. So we obviously, you know, only need 3 bits, but yeah, we only need 3 bits. You know, let's do something like that. That's all right. Oh, yeah, we only need 3 bits. So, what is this? E. No, it's E there, then 7 there. Right. So, yeah. So when we construct this as well, we probably want to make sure that the quad just 0 that, and all is well. So what we can do is we're going to initially build well, does it matter if 0 is there? We need to make sure there is a 0. Maybe not here, actually. Actually, we'll think about that one. So we bump allocate the new quad node index, right? It's a temporary one. I'm going to go ahead. So I've gone to the parent. No, sorry. I'm at the leaf node right now. We don't need to allocate anything. This is going to go to the parent. Yeah, I think I need to get rid of this do while loop. I did say this, I'll end up getting rid of this do while loop. It always happens. Scary. So if invalid fail. So I think when you go up to the parent, then you allocate that quad node index for the parent, so it can assign So now we can visit the 2 children and say that they link. So you visit the binary nodes, BVH. How do we get access to the 2 child nodes? So you go to the parent. And there's a left node index. And you say this quad word whatever. You'll get the quad word ready. Quad word 0 is going to be equal to whatever this is shifted by that shift. Like that. So we make sure that the bits at the beginning are set to 0. So when we atomically add to it, the visit count would be incremented. So we store that in there, that child, and then the right child as well. Right, that seems like it's coming together. So you're going up the binary tree, starting from the leaf nodes, you're going up and right, but I think we missed out on, where is it? Is that qualified 2? Perfect. So we need to get the number of grandchildren passed up. And so how are we going to pass this, the number of grandchildren? It will be a value between 0 and, 1 and 8 probably. So you can probably squeeze it into 3 bits. Which just makes things more cryptic, but okay. So when you go up this binary tree, you need to be able to pass up the number of yeah, but how am I going to visit the grandchildren if I don't have a temporary array where these nodes live? Yeah, maybe the strategy isn't good because I need a temporary array anyway. Because how could I? There's probably a good example somewhere, but yeah, here's one. If like this will all turn into one node of 4 children. This will go and this will go, and you have that leaf node, these 2, and that one there. Because you're going to get rid of that one, it will form 3 under this guy, and then you're going to get rid of this one, it will form 4 under this guy. So this would mean that, so we need to put these in a temporary array. Yeah, we need to put those in a temporary array. They are basically, unless they access it. Because when they're a leaf node, the number will change differently. But if it's not a leaf node, the siblings are 1 up from each other. Yeah, okay, so then we need to revert back to that other strategy we was doing. So you need to traverse up the parents and store the children in a temporary array. And while also storing the children in a temporary array, you need to keep track of the number of grandchildren, and that needs to be stored somewhere as well. So I think what we can do is use this as the number of grandchildren. So I think I think this is what we'll be doing instead. Right, so after you get so you go up to the parent successfully, you traverse up, you then need to, you can fish out of the left and right ones. You can say grandchildren 0, so for left, and then grandchildren right for 1. So that would just be something like this. Yeah, grandchildren count in it. And then we can get the total number of grandchildren by adding the two together. Then after we have the total number of grandchildren, we can then basically do this logic. So I guess I'll copy paste it. I just got to figure it out how we're going to do it. How we're going to convert it to the GPU. So let's put this in here. I guess we'll delete the other code that we just saw. Right, so it's not a recursive function, so we've got to be smart about it. So if the total number of grandchildren is less than 2 or greater than 4, you need to report back there's 2. So in your current node, in your current parent node, yeah, but what happens to the leaf node? Because the leaf node needs to set it, and you've already gone up to the parent. So what's going on here? Right, so this quad tree allocation thing doesn't have to happen yet. So we'll put that somewhere. So this code needs to actually happen. Right, but in the function it says if it's a leaf, yes, return 1. Right, okay, gotcha. So, yeah, so we need to know if it is a leaf, we need to get the number of grandchildren from somewhere else. So I think we'll move this up a bit, actually. Okay, so we get the number of grandchildren by saying if is leaf. So it's very... is leaf is equal to true at this point, and then is leaf equal to false after this. So we could maybe just go up to the parent and then make this more outside of this while loop, because I don't like conditionals where I don't have to do it. So we should probably set up the tree such that so you say equal to 1. So you'll set up the leaf node such that that is correct. You get your parent index or the visit bit. If the visit bit is not set, return. And the one that will carry on is the sibling that got there last. The sibling that gets there last goes up to the parent. I guess we do put that code before then. Goes up to the parent. Traverses up to the parent. Allocates that quad node index. I guess we can do that in a second. Gets the total number of grandchildren on the left and the right, adds them together. If there's less than or equal to 2 grandchildren, you can't really get rid of the left or the right child node because it's a leaf node, I think. Yeah, it'll be a leaf node. Is that right? Yeah. So you can't really do anything for the leaf nodes either. But then if it's 3 or 4, you can then start joining stuff together, I think. Yeah, and you'd always have, yeah. These would always return at least 1. So it all makes sense. So right, less than or equal to 2. Then return 2. That should set 2 in the grandchildren count node and then not do anything. And then continue, I guess. So you would do this, followed by a continue. Now, typically, I think continues don't compile to good code on GPU, so we might be better off doing a branch, like just doing an else statement. Yeah, because I remember performance checking that and it happened, but so I think we'll do this instead. And this is probably the... Anyway, we can micro-optimize it later, but I think this is better from my past experiences. So the problem is that we won't have the quad nodes at this point in an array. But this means that it is so this means that the number this means that it's either a leaf node here with 2, or it's already one with 4 or more. Yeah, or if you join the 2 together, it will produce one with 4 or more. Is that right? Yeah. So let's say you start putting so you get your left node index, your right node index. So that's the binary tree one. We'll do a children count. I guess we've got to store that somewhere as well. So we need to fish out the left node index and then a right node index. So fish that out. So depending on, so if you have more than one children on the left, we need to take all of the children now the number of children could be different, is that correct? The number of children in the left node. No, it should be the exact same number. Yeah, because it's the number of grandchildren. So you'll be looking at the left node. So my issue is, right, is you can't get them from the binary tree nodes, because if you look at this one will collapse this into 3, or that will go, this will become 3. So that temporary array of 3 has to go in a temporary array somewhere, right? So we don't really know if that's happened or not. So really, in this one as well, if it's less than 2, we should be moving it to a... So it's greater than 4, do that, and then if grandchildren count less than 2, less than or equal to 2, we're simply just going to copy it into the new array. So it'd be called like BC quad children, right? So it'd be that node index multiplied by 4 plus 0, and you'll put in the 2 nodes, which would be these boys and girls here. So you're going to reference So you always put in references to the binary tree children. Maybe that's wrong. Yeah, because ultimately, oh shit, what did I do? So you'll get the number of, it's all about retaining the leaves. And the leaves will then point to parents. So these two have to point to that parent. Then these two would point to this parent here instead. So you retain the array, so then you can change their parent. Yes. So maybe you do need to keep the parent as well, and then you traverse up. You need a temporary array. Oh, this is so confusing. Right, so we actually need to make sure. So that old thing does need to come back that we just deleted. It's alright. So grandchildren count. That will be a value from 0 to... Maybe I'm going to use some bits. But yeah, in the future we are going to pack... We'll pack this. Because it'd be like 1 to 8 or something, so we can pack into 3 bits. I think that should be doable. Oh no, we can pack into here, grandchildren count. But yeah, let's write this out quick, or properly first, and then we'll do the packing thing. Because yeah, we don't want to overdo it. We don't have to. Right, so where was we? So we need the array to store the indices for the children, but then we need to make sure that we set the parent index up. That's correct. So then we'll traverse up from the children a second time and allocate properly. Yep. So these get patched in there, but also you visit, well, nothing changed here. So you don't need to patch the parent. No, you do. So it'd be the new quad word 0. The way we do it is we pack via, yes, it's just shift in it. So your parent index is BVH binary node. So assign the parent index in there just like that. But you need to do it to the left node and then the right node. Okay, things are going along good. So here is when actually you've not just got, this is for a leaf node. This is for a non-leaf node where it's able to join multiple nodes together because there's enough room. This would mean so it's difficult. I guess we could store the number of children in the first node in the array. I don't know. Or you can maybe store it again in some of these bits here. Probably some packing thing you can do. But anyway. So you start the number of children off as 0. If there's grandchildren, we need to fetch so based on BVH quad node, times 4 plus, so in this case we're going over the number of, so I guess it'd be that. Will it be in a for loop? I think it might, you know. How do we get the child? So the left child is going to have, you know, having this different quad node index is just bananas at this point. I think we won't bother bump allocating it. We're just going to say every binary node will have another array where 4 children can sit. Well, why do it in another array? Why not just have it here? So then that would then mean, yeah, perhaps this is the way. Currently these are uninitialized if it's the leaf node. Yeah, so we could store them in here instead. And then we don't need a separate array. So we can move them around. We can reparent it, right? Reparent, and that should be okay. We just have a separate visit count. This could be heavily simplified then. I don't think we need to do any ultra packing here because We've already decided to make it kind of big with these anyway. But the grandchildren count would be needed as well. So maybe you can pack those, which you've already done with this quad word anyway. Visit count. And then children count. Yeah, I'm not sure how much packing it will help if we've just padded it out with this, to be fair. So this could probably be okay. Right, so it's really changed the tree now, but this would be easier. So rather than bump allocate and generating this, we're just going to be working with quad. So I think whenever we have the word binary, I think we can just get rid of that now, except for the array. And I guess BVH as well can just go. Right, okay, so we instead traverse up the tree, we up the visit count, and we can set that back to 0 afterwards, yeah. So we atomically add to the visit count by 1. So if visit count equals 0 with the first node, so just terminate there. Now we carry on. So we extract out the parent index. Then, so we go up to the parent. And what is this doing? Yeah, that's good, that's good. Before I forget, in the previous shader, we need to make sure that every node that gets set up, we need to set the visit count to 0. We also need to set the children count to 2. Do we need to? It's the same thing. You just return the number of children, right? All good. And if you're a leaf, it's 1, right? Leaf knows initialize it to 1 there, so it's children count. Will be set to 1. Okay. So this just looks at it by taking the children. So total number of grandchildren, if you have 4, then oh, misspelled of count there. Then the number of children you have is 2. and you don't change anything. So it just stays the same. It will just stay the same. So less than or equal to 4. We can then try and merge some of the nodes. But if it's less than, then we don't have to do the copying anymore. So it kind of becomes more like the CPU one that we did. So it should be able to be like this. So it's the opposite of this. So we're saying if it's greater than 2 and less than or equal to 4, then we'll merge. So no longer do we need to allocate. I guess that can stay there, that's cool. No longer do we need to allocate. We get the left and right node for this parent, left and right children for this parent. That can go. Right, it's all pretty easy from here. Children count back to 0. If we have any grandchildren on the left, we will get the left node. Gotta be careful here. What is that doing? Get the number of children on the left. No, which is same as this. So you go over that, and then you need to access the left node children. So we need the I think it's indices, isn't it? What did I call it? Children indices, that'll do. So you get the children index. You go over all the children and copying them over. Then you're incrementing your children count. So this will get stored in BVH. And you increment, yeah. So then, same thing here, but then you're storing the left node index instead. So if you have a single grandchild from that node, you just put on the left node index. So it's the same thing, but for the right hand side now. So we just got to be careful. So rather than 0 and 1, it could just be called, left and right. Right, and then that'd be right. Right, then we need to store the children count back into the node. Now that took a bit to work out, but that seems like, yeah, it seems a good way to port it over. We're just going to have a fatter binary node, which is not really a binary node anymore. So perhaps we should call it the BVH build node, and it starts off as a binary tree, turns to a quad tree, and then we pack it down, right? So yeah, I think we should rename this to a build node. Just makes a lot more sense, you know? BVH build node. Build nodes, plural. Right, so in the internal build nodes, size of build node. Yeah, that's a lot better. So we can say in the comments, starts off as a binary tree, So initially this is built as a binary tree. Then it's turned into a quad tree after, okay, used in the build process of the BVH tree. Initially is built as binary tree, then it's turned into a quad tree after it is packed into a BVH node. Right. Okay. That's better. So construct find children. So we say build binary tree, build quad tree, and then pack. Those are probably better names. So build binary tree. Reparent as quad tree, or build quad tree, right? Hey Kilobyte, appreciate it, sir. See is the way. When you see, you see. Do you program in C, Kilobyte? Yeah, so that's good. Right, should we double check this shader and then get it off the ground? What the hell is that? Oh, what are these thingy-majigs? Goodbye to you. U32 max now is the invalid node. Right, so we dispatch every thread is a leaf node, and then we traverse up the tree. Right, this comment's wrong now, but anyway, we'll correct that. So start off with the leaf nodes, set this leaf node to there's one child. Doesn't really have one child, but yeah. This leaf node doesn't really have one child, but it is part of how the code works below. So you up the visit count. Oh, I've got to remember to clear this visit count out actually. So here's success. Clear it back out for the next shader. So we just store it in there like a champ. Reset it for the next shader. For the pack. Pack quad tree. That construct refit is not going to be reusable, which is fine. I didn't want it to be reusable, specifically. It didn't have to be reusable. So refit would be its own thing on the side, I think. Yes. Makes sense. Alright, so then we extract out the parent index, go up to the parent, look at the two children left and right, get the grandchildren count. So this just to keep it consistent to how we've written the code so far. Right. So then we say if there is in between 3 and 4 children here, it means we can take what the crap is that about? What? This should have moved up to the parent. Yeah, move up to the parent. Yeah, move up to the parent and then say while node okay. Visit count. So we visit the parent. So I guess you don't need to do this here. This happens at the end. No. Alright, we'll check if that's good in a minute. So move up to the parent. Yes. While not equal to invalid. Could that ever be the case? Well, you could have one leaf node, which means one parent. So yeah, but if you only have one node, we shouldn't even launch this shader anyway. Because it's already a tree. That's something to be aware of. Yeah, we shouldn't even do anything at that point. Anyway, visit switch to Python for cybersecurity. Okay. I'm doing my first war game on Over the Wire. Bandit. What is Over the Wire? Bandit. I've never heard of that. So you up the counter with the second thread to go through, carry on, reset it for the other shader. We don't need that anymore, so we left, right, yep. If we're in between 3 and 4, so I guess we can do it like wherever we're in between 3 and 4. You could probably do that in a nice hack actually, right? Or if 3 or 4. Right. You can remove... What's the best way of saying it? You can probably do some nice hack where you say and the bit off. Add 1. I don't know if it's even better, to be fair. Let's make it readable. Because you have to do 2 things. But yeah. We'll do that for now. So children count equals 0. If your left grandchildren is greater than 1, take all of the grandchildren out and store them in this parent node. So we're just incrementing and then we're fishing it out of there. Neat. So if there's only 1 child, we just put the left node there instead. So we don't get its children out because it'll be a leaf node basically. A nice hack would be the following, right? If it's a leaf node, store its own number in there, but there's no point in a previous shader where we even touch the leaf nodes. So it's actually not possible without running another shader. So it's probably, otherwise we'll just get rid of that and just run this, right? But I think we'll keep the branch in there. Something we could play about with in the future if we want to hyper optimize it maybe. But I don't know if it's possible. Anywho. Right node greater than 1. That seems legit. And that's legit. So now we've we've built the new build node. And we set the count up. Cool. Then go up to the parent. And that's legit. You keep going up. Will you terminate or... Okay, that's good. So, something to be aware of is... right, this is all we need now. If this is a leaf node, as we start traversing leaf nodes. Currently these uninitialize when it is a leaf node. Yeah. So the whole leaf node is actually uninitialized. And the only time it gets initialized, oh crap, we can poke it in here. Which means we can initialize everything. The visibits will be uninitialized. Parent will be set. Oh, this is going to be legit. We can store in there. We can store in here. And then it should... Well, you didn't write out to memory. But it might be good. Yeah, it keeps it. Yeah, it makes the code more simple, right? So I'm all for that. Makes it easier to follow, right? We're just copying them in. So we can say like, oh, join. You need to update the parent indices. We forgot about that. Go down to the children, update parent. Join the 2. Yeah, the issue is you'll go down to the parent in here though. You're doing more memory writes. Yeah, I might undo that. I don't know how much better it actually is. We can see later. Yeah, we forgot to write out. So this child index that you've got here, that child index that you have there, we need to make sure that you set the parent index to be node index, such that when we start look from the bottom of the tree a second time around, we will just go up the quad tree and then just pack it down. Yeah, so we actually need to, whereas this one, the parent node will already be set properly. So we don't need to do that. Okay, that's it done. So should we take a look at the, let's get that building quick. Ooh. What's going on here? Right, so basically, this is known as the build binary tree. That's the new name for it. Build binary tree. Nothing really changed, just the name. We then copy paste this and change it for a. That's. Alright, we should change this name. CS BVH build binary tree BC. 8. So the other one is called, yeah. So BVH build quad tree BC. Whatever, right? So the way this one works is that it just needs the build nodes as read write, and we don't need anything else, I don't think. Oh, we need the number of leaves. You need the number of leaves as well. So it's a very small amount of information. So we just make sure we mark that as read write, that build nodes resource, and the global buffer as well, probably read write. Actually, we don't need that as read write. What'll be interesting is if we didn't have to sync on that here. Because in the frame init, it initializes that there properly. Neat. And then when we finish, we'll clear it to 0 as well in the final shader, in the pack shader. Neat. So this will build the quad tree instead. There'll be another one called pack quad tree. Which we haven't written just yet, but it'd be pretty similar, goes from the bottom all the way up. But let's just test and make sure that this does run and it builds a quad tree that we're expecting. So this one, Should be quite easy to verify. We launch over the number of leaf nodes though here. This is wrong. Alright, so... Right, so if the stream dies, I'll be right back. Right, we're still running. So it should have built this tree. No, it built this tree on the GPU, the binary one. But it's also got to update it to the quad tree. So it will quadify this. So what we're going to do is open back up the... Alright. Here it is. So we're going to run the quadify on the CPU and see the visualization. So it should have built this tree on the GPU. So we're just going to verify that it's true. So I'll take a screenshot of F12. We can open that up in the in an image viewer of choice. Here it is. And now we're going to open it in RenderDoc. So giving it a run. Does a capture. So in the compute dispatch 2 where there's that barrier, oh, there'll be a third one now. Don't know why there's not a barrier. Oh, there's a barrier. All right, it's cool. Anywho, BVH build nodes. So if you look at this, it's not a binary tree anymore. We need to delete some of these. Right, so it's called the BVH build node. And it's going to be, right, strut. I can just tab it. BVH build node, where you at? Right, so parent index children indices 4 visit count and children count. Boom. So we apply that, and here we go. So yes, the root node has 2 children, 16 and 17. Oh yeah, that seems to have worked. So let's keep having a look. 16, 17. Oh yeah, progress. So amazing. So node 1. Is this even on the tree? Because the issue is we're going to have missing ones and we're not going to know what they are. So let's just find a 16, for instance. Let's just follow it down and see what happens. So 16 has 4 children. Yes, 2, 3, 12, and 13. Yep. So then let's follow like 2. 2 has a parent 16. Yes. 3 children, 31, 2, and 33. Yep. So if I look, so we're getting the right tree. Let's look at 13. 4 children, 44, 45, all the way to 7. Yep. Let's look at 20. 50, yeah, 2 children, 51 and 52. Sweet. Let's look at this one, 28. 59, 6, yep. Yep, that's good. Over the Wire is a site that hosts war games, basically capture the flag. Oh, okay. Right. Okay. What, so is it to do with like cybersecurity and stuff? With, that's interesting. Is it true? Huh. What is it for? Is it just a game? So what does this program do? It builds, I'm building a BVH on the GPU in a highly parallel manner. So that's all it does basically. And we can use it to ray trace against, so it'd be an acceleration structure for ray tracing. So I implemented it on CPU. So here's an ellipsoid that we're rendering. Just we're doing rays versus ellipsoid, and it's got PBR. We need to fix the anti-aliasing. Here's an environment map in the background, and see there's a reflection of the environment map on the ellipsoid. So we're currently building a BVH, so we will be able to traverse down and ray trace against tons of ellipsoids, and it hopefully will be quick enough to render a game. So that's what we're working on. So the next one is to build a BVH. Actually just pack it in and build it, right? And also construct the, oh, I didn't change the comment. So this will construct a quad tree from the binary tree by relinking the parents and copying the children. So the leaf nodes will stay copying the children indices. We start each thread on a leaf node of the binary tree and ascend up the parents while terminating one sibling thread at a time. So yeah, so that's good. I'm glad that works. It's a bit complicated to get that in. I was trying to make my binary node as small as possible and thinking I needed another array to store these temporary children nodes. Well, that's the thing. I went from this shader thinking I could just construct the quad tree all in place. It all packed in and everything, but it turns out I needed another pass. So we're just we have a build node now. With a build node can be a binary tree that gets turned into a quad tree. And then after we've done that, we can do the packing one, which is going to generate a packed binary node which fits into 16 bytes. And it has a whole ellipsoid information in it as well. So this is what we're going to do next stream, is pack this generate this packed BVH node data structure. We already have all the functions for it. And I want to double check and make sure that the quantization is a good idea. I just want to rethink that part because I've forgotten about it. And then after that, we should have a fully constructed BVH tree that we can then ray trace against and visualize it. Yeah, and then visualize it basically. Yeah, I think we want to have a special case to say if to do handle single leaf node BVH tree, because my shaders are not built to handle that, so we can handle it. Awesome. Right. So the next stream will be on Tuesday at 7:30 p.m. GMT +1, where we're going to finish off that final compute shader to construct that BVH, and then I'll probably record a devlog as well at the, after we've done that, so we can put that up on the YouTube channel and people can be caught up that way. Yeah, so after that we'll do some ray tracing also. So yeah, right, so let's find someone to raid quick. Then the basics of Linux commands. Oh, okay, fair enough. Let's raid this dude. Right, have a great work week, everyone. Hopefully see you on Tuesday or Thursday. And yeah, thank you all for coming. I'll see you in the next one.